Welcome to this lesson about continuous random variables. Last week we talked about the discrete. So we have two types, the discrete and the continuous. And what is a continuous random variable? Assumes values in a set where we cannot put the elements in correspondence with the natural numbers. We cannot put the elements in correspondence with the natural numbers. This is a very big definition, but it is easy to understand. Because last week we talked about the variable number of faces when we draw 2 coins. And that variable can assume the values 0, 1 or 2. So, the variable can assume the value 1, 0, 1 or 2. And here we can say what is the first, the second and the third. So we are making a correspondence between the elements of the set and the natural numbers. Okay? We can identify the first, the second and so on. But when we are dealing with variables that are continuous, for example the weight, I can write, for example, 80 kilograms. 80 kilograms. And now we cannot say what is the next value, because if we can put here, for example, 80.1, but then we can choose always one in the middle. For example, between 80 and 80.1, we have, for example, 80.001. And we can do that always. So it is impossible to say what is the first, the second, and so on. So we cannot assign probabilities to each specific value. But here I can do, when we have a discrete random variables, for example, probability of 1 is 2, probability of 0, because I'm talking here about 0. The first possible value, it's 1 divided by 4. Probability of 1 is 2 divided by 4, and probability of 2 is 1 divided by 4. And we don't only use a probability function when we have a discrete random variable. Because the continuous, we use intervals, and we can only give probabilities to intervals, okay, with the continuous random variables. But a continuous random variable has two functions. So continuous random variable has the distribution function that we already know what it is. So the distribution function. And what is the distribution function? It is the BF of the random variable x, and it's equal to the probability accumulated until the input in the function. So probability that the random variable assumes a value equal or lower than the input in the function. But now with a continuous random variable we cannot have a probability function, but we have a density function. And what is the density function? The density function is the derivative of the distribution function. So it's the derivative of the distribution function. So we can write in a mathematical notation as, I will write small f for the density. If we are dealing with continuous random variable, the small f is the density. If we are dealing with a discrete, The small f is the probability function. But here is the density and is the derivative function of the distribution. Okay? So, but now it's important to review what is the derivative function. Okay? You have talked about derivatives in the first semester because you had mathematics in the first semester, but I will review what is important about the derivative function. Okay? So we'll bring this part here, and I will talk about two types of derivative. Two types, okay? It's the derivative in one point and the derivative function. So I will talk about the derivative in one point. I will review the idea, and then about the derivative function. So, what is the derivative in one point? So, I recall that I'm talking about derivative because density is a derivative. Okay. So, and what is the derivative in one point? I will use the very well-known example of the function x squared. It is a parabola, okay, parabola. Under the graphic, we know very well how is the graphic of x squared. So is this parabola, okay? And when I want to get the derivative in the point with first coordinate equal to 2, point here with first coordinate equal to 2. So this point here. What is the derivative in that point? Is a slope of a straight line. Okay? When we have a straight line, for example, I will write here 2x. So this straight line is very well known. The slope is 2. When we move one unity to the right, we move 2 up. Okay, so here. So this is a straight line with slope equal to 2. Okay? So, but the derivative is a slope of a straight line. But what straight line? The one that is tangent in the point. So it's the slope of the straight line that is here tangent in this point. So the derivative is the slope. The derivative in the point with first coordinate equal to 2. Okay? But now we can use a derivative function. And with the derivative function, we can get very easily the derivative in any point. For example, here I have this function, x squared. But the derivative function of x squared is equal to 2 times x. And now, with this derivative function, I can obtain the derivative in any point. I only need to replace the x by the first coordinate of the point. For example, here I want the derivative in the point with first coordinate equal to 2. I put here 2 as input in the derivative function. So x I will replace by 2, and I get 4. So that is the reason I said to you that the derivative in the point here is equal to 4, the slope of this tangent line. But if I want in the point with the first coordinate equal to 3, for example, here, this point here, the first coordinate equal to 3, how I get very easy the derivative in that point? I use the derivative function, and I put here, instead of x, I will put the first coordinate of the point. So I get 2 times 3, 6. So I know that the slope of the tangent line here in the point with first coordinate equal to 3, the slope of this tangent line is equal to 6. And now if I move to the left of 0, if I move here, like for example here in -1, I have here a point with first coordinate equal to -1. What is the derivative? Here is negative because the slope of the straight line that is tangent is negative. So I have here a negative slope. And how I get the slope of the tangent line? I use the derivative function. So I forgot here to put the symbol of derivative. Now I will do the derivative in point with first coordinate equal to -1. So the result is 2 times -1, -2. So the slope of this straight line is -2. Okay, so you already review how important is the derivative function, because with the derivative function we can get derivatives in any point very fast. Of course, there are many other applications of the derivative function. I can review very fast two that are very important. For example, one application of the derivative function is if I have, let me see here, this function, like this. When the derivative is positive, what is happening to the function? Is growing. For example, here, the tangent lines, the cliffs are positive. And when the function is growing, the derivative is positive. Okay? The cliff of the tangent lines are positive. But, for example, here, the function is decreasing. And when the function is decreasing, the derivative is equal to what? Is negative. Okay? So when we have a negative values for the derivative, the function is decreasing. When we have positive values, the function is increasing. So to analyze the behavior of a function in terms of growing or decreasing, we can use the derivative. But we can use for also to get the maximum or the minimum of some function. For example, those problems are important in economics, of course. Many times we want to search for minimum costs, for example, or maximum profits, and we can deal with the derivative. For example, what happens when I have a maximum here? What is the slope of the tangent line in a maximum? The slope is equal to 0. Slope equal to 0. And the same in a minimum. So here the slope is also equal to 0. So we can also use the derivative function to search for points that are maximums and points that are minimums. But there are other applications of the derivative function. But the one that we want today is the density function. So, but to do a first simple example, I will review how to get a derivative function. So, for the exercises that I put in the Moodle, you only need 5 rules to obtain the derivative. Only 5. So I will put the rules here, and they are very simple. You have talked about many rules in mathematics, not only 5. Okay? But we will use 5 that are very simple. So 5 rules to obtain the derivative function. So the first rule is for the derivative of a real number. I will go k. So the derivative of a real number is always 0. So here k is a real number. K is a real number. For example, if I have the function f equal to 3, the derivative of 3 is 0. So, now the second rule is when we multiply the x by a number, real number. So for example, k to kx. So when we multiply a real number by x, the derivative is the real number. So very easy. For example, if I have the function 7x, the derivative of this function is 7. Rule number 3. Now I will do here what? The derivative of the sum or subtraction. The derivative of the sum of subtraction of two expressions that can involve x or not. The derivative of the sum is equal to the sum of the derivatives. And rule number 4, I will use here a simplified version that you gave in the first semester, because you don't need to use the more complex rule. You only will need to use this simplified version, that is x with exponent k. K is a real number, and the derivative is k times x with exponent k minus 1. And the last rule is for number 5, when you multiply one expression that involves x by a number, by a real number. So I will write this as k times u. Derivative. So very easy. We move the k out of the derivative and we get k times derivative of u. So let's give here some simple examples. For example, if I have the derivative of x with exponent 7, how I calculate the derivative? So it's rule number 4. Now we have here x with exponent equal to real number, so k equal to 7, and we apply the rule number 4, and we get 7 times x with 7 minus 1, so the result is 7 times x with exponent 6. Okay? Very easy. Now you understand why the derivative function of x squared is 2 times x, because we applied the rule number 4. So, what is the derivative of x squared? We have used that function today. The derivative is applied. We apply the rule number 4 with k equal to 2. So we get 2 times x with exponent 2 minus 1, and we get 2 times x. So now you can understand why I have used 2 times x as the derivative function of x squared. Okay? But let's see here rule number 5. Rule number 5. Let's put here one example. For example, if I have 6 times x with exponent 3, how I calculate this derivative? So we apply rule number 5, because what we have a k that is equal to 6, and we have an expression that involves x. And what is the expression? That expression we call u. The expression is x with exponent 3. So the u here is x with exponent 3. So we apply first the rule number 5, and we put out of the derivative the k, and we write 6 times x with exponent 3 derivative. And now we apply rule number 4, because this one here, we have this form, x with exponent k. So, and we get x times 3 with x with exponent 2, okay? Because I'm doing what? K minus 1, so k here is equal to 3, 3 minus 1 is 2. So the final result is 6 times 3 is 18, okay? Here, 18 times x squared. So very easy. Let's do only one example to finish this very short review about the 5 rules that you need for the exercise. So let me put here one example. For example, I want the derivative function of 2 times x plus 10x exponent equal to 4 plus 7. So how I calculate here this derivative, the derivative function of this polynomial. How I do that? I need to apply all the rules. Here I need to apply all the rules. I start by rule number 3, because I have a sum of 3 parcels, and the derivative of the sum is the sum of the derivative. So I will write derivative of 2x plus derivative of 10 times x with exponent 4 plus derivative of 7. I applied the rule number 3, and now here I apply rule number 2. We have a k times x. So what is the derivative? K. So we get 2. Here I need to apply 2 rules, the rule number 5 and the rule number 4. So I will apply first rule number 5. What I do? I put outside the derivative the k. So I write 10 times x with exponent 4 derivative. Plus derivative of 7 is the first rule. Derivative of a real number always equal to 0. So get here 0. And now I need to do this derivative, x with exponent equal to 4. It's now the rule number 4. So we apply it, all the 5 rules in this simple example. So here I get 2 plus, now 10, and here the derivative is equal to what? So I apply rule number 4 with k equal to 4, so I get 4 times x with exponent 2. And now I can simplify, because I can calculate 10 times 4 is 40. So, and we get 2 plus 40 times x with exponent 3. So this here is the derivative function of this here, okay? So let's now move on to 3 rules that we can use to calculate probabilities with the distribution function. But why I will talk now about the distribution function? It's important because the rule number 3 we will use to understand the rule of the density as a graphic that we can use to calculate and to observe probabilities as areas under the graphic of the density. So let's now give the 3 rules to calculate probabilities with the distribution functions. I write here 3 rules to calculate probabilities with the distribution function is the big F, okay? With the big F. The first rule is the direct application of the distribution function. So if I want to calculate the probability accumulated into the volume, big X, lower or equal than small a, we only need to apply the big F. Okay. We already know that big F with input equal to a, it's what? Is the probability accumulated until the value a. Or in other way, we can say that is probability that random variable assumes a value equal or lower than a. Now the second rule is for the complement. What is the complement of x lower or equal to a? Is higher, so x higher than a. And here we use the complement theorem. The probability of the complement is 1 minus the probability of the event, and we can do the same with random variables. So we write 1 minus big F evaluated in A. But now the number 3 is the most important, because with the rule number 3 we can do everything. We can do everything. It will be for an interval between A and B. So I want a rule to calculate probabilities with the distribution function, but the probability for an interval between A and B. And we only need to do what? We calculate here the distribution function with the input equal to the upper limit B, less or minus, not less, minus the distribution function with the input equal to the lower limit A. So this is a very simple rule. We use only distribution function to calculate probabilities in any interval. So with the continuous random variables, we are dealing with probabilities in intervals, because it's impossible to give a probability to one specific value. And by definition, the probability of one specific value in a continuous random variable is 0. So we deal only with probabilities in intervals. So, but why I talked about especially the number 3 rule, I'm going to explain that now. So I will keep here the rule number 3, and now I will talk about the integral between two values. For example, when we write the integral between A and B of some function in order to the variable x, what is the meaning of this? Before I put here the meaning of this, I will put one specific example. It's more easy to understand or to review, because this is a topic that you talked about in semester 1. So, but let me put here the function x squared. Okay? Very well known function x squared. And if I write the integral between 0 and 2 of this function, the integral between 0 and 2 of x squared in order to x, what is the meaning? The meaning is, the important thing about the integral is that it is an area between 0 and 2, above the x-axis and below the graphic of the function. So if I put here the graphic of the function, so we have the parabola here, and now between 0 and 2, the integral between 0 and 2, what is the integral? Is the area that I'm going to paint here, is this area, okay? This area is equal to this integral. Okay? So I will interpret now in a generic situation where the interval is between A and B, and the function can be any function. I write the meaning of this integral is the area between A and B above the x-axis, and below the graphic of the function, and below the graphic of the function small f. Okay, but now how you have done the calculation of integrals in the first semester. How you have done that? You used the fundamental rule of integral calculus. And with the fundamental rule of integral calculus, we need to use the primitive. But what is the primitive? What is the primitive? Because here to calculate this integral, we will use the primitive of f, that we call big F, evaluated in the upper limit, minus the primitive of small f evaluated in lower limit. And this is what we call the fundamental. This all here is the fundamental rule of integral calculus. But what is the primitive? What is the primitive? Let me give you and review that with a very simple example. If we have the function equal to 2x, we have this function 2x, what is the primitive of this function? We don't have only one, we have infinite primitives, because the primitive is a function that when we calculate the derivative, we get the function. So we can have many functions. For example, all functions that are equal to x squared plus k, all those functions, if I calculate the derivative, I get 2x. So if I do the derivative, what I need to do, derivative of x squared plus derivative of k, and we get 2x. Okay? So, if I said to you that the 2x is the primitive of x squared, for example, I'm changing. It's the opposite. The x squared plus k, but I can drop the k, because if I want only one primitive, I can drop here the k, and I can say that x squared is primitive of 2x. And when x squared is primitive of 2x, 2x is the derivative of x squared. So the relation is very simple. When I have a function that is the derivative of other, x squared is the primitive of other, x squared is primitive of 2x, then 2x is the derivative of the other. So one is the primitive, other is the derivative. So the relation between the distribution function and the density is this relation, because I said to you that the density is the derivative. Density is the derivative of a big F. So if the small f is the derivative of big F, then the distribution function is the primitive of the density function. This is the primitive of small f. So if now here, I'm talking here about any type of function, can be a density function or not. But now I will put here a small detail, because I will put here big X, and big X, and when I do that, I'm now talking about the small f now is a density, and now the big F is a distribution function. And when we evaluate here the distribution function in the value b and minus the distribution function with input equal to value a, what we get here. When we do that, big FB minus big FA, we get the probability that the random variable assumes values between A and B. So we get here the probability. So this result, this idea is one of the most important in statistics and data analysis. Okay? So it's important for you that you understand well this idea. So this is the probability that the random variable assumes values in the interval between A and B. So now when we look to the graphic of density, what we know. For example, let's suppose we have this graphic. This is the graphic of a density. And let's suppose here we have 10. And here we have, let's suppose 20. And then here, let me put 30. And here 40. So, when I look to this graphic, because the probability in an interval below is an area, the probability between A and B is equal to what? Is equal to area between A and B above the x-axis and below the graphic of the density. So if I wanted to calculate the probability between 10 and 20, what I need to do? I can apply this rule, and I can do like big F of 20 minus big F of 10. Okay? I can use the distribution function, but I can also use the density, because this probability is the area between 10 and 20 above the x-axis and below the graphic of the density. So the probability here is equal to this area. Okay? And if I ask you, where we have more probability? Between 20, 10 and 20, or between 30 and 40? Near the center of the density or in the tail? Of course, the area here is much lower, much more small, much more less area. So the probability, the random variable has a much higher probability in the interval between 10 and 20 than in the interval between 30 and 40. Okay? This idea is really very important, and we use this way of thinking a lot of times when we are dealing with data analysis. But now let's solve one exercise of the group of exercises that I put in the Moodle. We have enough time. I will solve the exercise number 6. So I will put here exercise number 6, and we will apply this to a specific example. So exercise number 6. I gave you a distribution function. I will write here distribution function is is 0 for real numbers below 0, for x lower than 0. Then 1 divided by 4 times x squared for the interval between 0 and 2. Between 0, I think I put like this, and 2. And then is 1 for real numbers above or higher than 2. For x higher than 2. Here you can put like this. So, as always, the distribution function starts at 0 and ends in 1. 0 for values lower than the first possible, and 1 for values that are equal or higher than the last possible. But now, what are the questions? Let me check here the questions. So, exercise 6. The first question is for probabilities in 2 intervals. I will do only one of them, because the other is in the same way. So, first question is probability that x assumes values 0.1 and 0.3. How we calculate this? We use, now here we will use the rule number 3 to calculate probabilities with the distribution function. So what we do, the big F in the upper limit minus the big F in the lower limit. And now I need to apply the distribution function. So it's the output of the distribution function here with input equal to 0.3. Both 0.3 and 0.1, both are between 0 and 3, so I apply only this expression. So I will do 1 divided by 4 times 0.3 squared minus 1 divided by 4 times 0.1 squared, and I get a very small probability. Only, if I'm not wrong, 0.02. Okay, so this is very easy. Now you can do the same for the other interval. The difference in the other interval, what is the difference? It's between 0.9 and 1.1. So I will change here the interval. Now it's 0.9 and 1.1. And the only thing I need to change is what? Is here. Instead of 0.3, I will put 1.1. And instead of I don't have here 0.1, I put 0.9. And if you do the calculation, you will get a higher probability. I will explain why. Because we have more density. We have more density in this interval than the interval between 0.1 and 0.3. Now let's move to the second question, is to calculate the density, I suppose, yes, and represents the graphic. So question number B is density. So I want density. So it's the derivative of the distribution. So small f is the derivative of the distribution function. So I need to calculate the derivative of the big F using the rules that we talked about some minutes ago. So I will do the derivative of this part, this part, and this part. Here, because all functions are all continuous, you don't need to pay attention to the derivative in the left and the derivative in the right. You only need to use the rules. So here I will do the derivative of 0. 0 is a k, is a real number, so the derivative is 0. Then I need to do the derivative of 1 divided by 4 times x squared. We already have done some very similar to this here. What we have, rule number 5, k times a u, an expression that involves the x. So we put the k outside in the derivative, 1 divided by 4, and we calculate the derivative of fx squared. Oh, but this, we already know the derivative is 2x. So we get 1 divided by 4 times 2x, and we can simplify and write 1 divided by 2 times x. And this is for what is the interval? Between 0 and 2. So I'll put for the interval between 0 and 2. And now the other intervals, they have all derivative equal to 0, because derivative of 0 is 0, and here derivative of 1 is also 0. And now we can write in a very short version the derivative of the distribution function, the density I will put here. So small f is equal to 1 divided by 2x for in the interval between 0 and 2. Oh, I'm doing here a mistake, between 0 and 2, and 0 for other values. So we write O dot V dot other values. Now I want the graphic of the density, because the graphic of the density is the most important thing about the density. So let's do it here, the graphic of the density. So we have what? We have a straight line with slope equal to 1 divided by 2. So I can do here a table if you like. Because if x is 0, what is the second coordinate? 1 divided by 2x. So 1 divided by 2, 0 is 0. So we have here this point 0, 0. And then I can move here to point 2. What is the second coordinate? I use the expression for the straight line. So if x is equal to 2, we get 1 divided by 2 times 2, we get 1. So we have here this other point, and with 2 points we can represent a straight line. So, but we only represented the straight line between 0 and 2, because the expression of the straight line here is only valid in the interval between 0 and 2, because outside this interval the output is always 0, the density is always 0. So, and now it's very easy to understand why the first interval here, the probability was only 0.02, and the second interval I think is between 0.9 is here, and the probability is much more higher, because the area between 0.9 and 1.9 is higher than the area between 0.1 and 0.3. But now, question number 3, it's a probability in an interval using, C is a quantile. I will move to D, and then I will talk about the quantile in the end of the lesson. So I will solve now question number D. And what we want in question number D? We want the probability that the random variable assumes a value between 0 and 0.75. So I can say that. Let me confirm here. Yes, between 0 and 0.75. So, and now we know that the probability in one interval is 1 area. So this will be 1 area. And here, because we have triangles, we don't need to use the primitives to calculate the area. Only the last 3 exercises you will need to use, I think is 2 simple rules to calculate the primitive, but only in the 3 last exercises. It is, we don't need why, because we want the area between 0 and 0.75 and below the graphic. So what we have here? Here we have a triangle. So this very small triangle is equal to this, probably not the triangle, the area of the triangle. So, and now the area, the probability between 0 and 0.75 is the area between in the interval above the x-axis and below the graphic of the density. So we know very well how to calculate the area of a triangle. Is base times height divided by 2. So I will need to calculate the area of the small triangle, so the area of the triangle, and the area is base times height divided by 2. The base is equal to what? The triangle is between 0 and 0.75 is equal to 0.75. And now the height. What is the height of the triangle? I need to get the second coordinate of the point with the first coordinate equal to 0.75. So I need to get here the second coordinate of this point here. And how I do that? I use the function. So to get the second coordinate, I use this function here, 1 divided by 2 times x. So I have the point with first coordinate equal to 0.75. I want to get the second coordinate here. So I do what? 1 divided by 2, x. So I do 1 divided by 2, 0.75, and I get 0.375. So here the height of the triangle is 0.375. And now I know the base of the triangle, I know the height of the triangle, and I get easily, I think this is about 0.14. But please do this calculation. I think it's about 0.14. Okay. Now I can ask you another example to consolidate the idea. Let me do. We have time. We only have 12 minutes, so we have time. So let's do other example. It is not in the exercises that I gave to you, but I will ask you now an E question that is not in the exercise. I want the probability between 1 and 2. Between 1 and 2. Between 1 and, let me put here like this, 1 and 2. And what is the probability between 1 and 2? Now, I will clean this, the D, so we already have done. And now I will clean also here, because now we want the interval between 1 and 2. So we are talking about the area between 1 and 2, above the x-axis, and below the graphic. So is this area here? This area. Oh, but now I calculate this area. I can use this triangle here, and I can add the area of this rectangle. But it is not the most intelligent way to do it, because why? Because the complete area of the triangle that represents the total density between 0 and 2, what is the total area? Of course, must be always 1, because the probability maximum is 1. If you calculate the probability for all possible values, you need to get 1. It is easy, because this triangle here, the triangle, what is the base? 2. Base 2. What is the height? 1. And we divide by 2, and we get 1. So the area of the complete density, the area is 1. But now we want the area between 1 and 2. What is the most intelligent way to do it? Is to do the 1 complete area and then subtract the area of this triangle here, the white part. So I will do the probability between 1 and 2 is what? 1 minus the area of the, I will write here, of the white triangle, this triangle here. The complete area is 1, but now we subtract this area and we get the black area. Okay, that black area is the probability that we want. So we subtract area of the white triangle and we get 1 minus. So area of the triangle is what? Base. What is the base? The base is between 0 and 1. So the base is 1. What is the height? I need to get the height the same way I have done here. But now, what is the first coordinate? The first coordinate equal to 1. And we get the height of the triangle by getting here the second coordinate. And if the first coordinate is 1, the second is 0.5. 0.5. So here, the height of this white triangle is 0.5. And now it's very easy to do the calculation, because we get 1 minus, so here we will have 0.5 times 0.5, it's 0.25, and what we are saying here is that the area painted with black is equal to 0.75, and this area in white of the white triangle is of course 0.25. And what we are saying in terms of probabilities, that probability between 1 and 2 is much higher than probability between 0 and 1. Here the probability is 0.75, and between 0 and 1 is only 0.25. So I think we still have 7 minutes, but I only need 2 or 3, because to finish now the lesson, I will not solve the exercise 6C. It will be like homework, but I will give the definition of quantile. Okay? When we are dealing with random variables, usually we define a quantile in a different way than what we have done with empirical quantiles. So I will define here quantile P. Quantile P. And what is the quantile P? I will denote by, if for the random variable with x, I will denote by small xp. And I will say that the probability that the random variable assumes a value until the quantile is equal to 1 minus p. And I can also put this way. I can write big F of the quantile is equal to 1 minus p. But now I will give a graphic, because with the graphic it's more easy to very fast understand what is the quantile. So I will put here a density. So this is a density. And now I will put here the quantile P. And what happened with the quantile P is a value, such a value where the area to the right of the quantile and below the graphic of the density and above the x-axis, this area is equal to P. So this area is equal to P. So what is the meaning? The meaning is that the probability, I can write instead this way, I can write probability that the random variable assumes a value in the interval between the quantile and plus infinite, the probability that the random variable assumes a value higher than the quantile is P. Of course, if probability that assumes a value higher is P, the probability that does not exceed the quantile must be 1 minus P. So, in front of the quantile we have a probability equal to P. To the left of the quantile we have a probability equal to 1 minus P. So now I only will put the exercise 6 and C as homework. So for you to try to do this exercise as a homework. And here we want 2 quantiles. We want the quantile 0.25 and we want the quantile 0.75. 0.75. What is the quantile? I will put only one of them here. It's between 0 and 2. What is the quantile 0.25? It's a value here. The value must be not far away from 2, because I want the area. So the value will be here, the small x 0.25. What I know? I know that the area to the right of the quantile and below the graphic, this area must be equal to 0.25, but of course the other area must be 0.75. So what you know to solve this question? You can use the triangle with base between 0 and the quantile. And now you know know the area of the triangle, and what we don't know is the coordinate, the first coordinate, and then the second coordinate also depends on the quantile. So now you know the area, but you don't know the base, and you need to solve the problem. Okay, so that is homework. So we will finish now recording the video, and if you have questions, we still have 2 or 3 minutes. You can ask some questions now.